right, so let me start the presentation actually. So today I want to, first of all, actually thank you for coming to this presentation. And today I want to talk about the SoftFlash, the programmable storage in future data centers. So I'm Jay, I'm a researcher working at Microsoft Research. So before going into too much details, actually there are a few things actually I want to talk about. Again, thanks for coming to this presentation. And second, unfortunately, actually, recently I have started some treatment for aligning my teeth, so my pronunciation or speaking might not that be accurate. So if you don't understand what I say, please raise your hand, and I'll try to be my best actually to be as accurate as possible. And the real thing I want to say here is actually my background is in database, not storage. So to achieve the goal of this project. Definitely I need a lot of help from storage experts like you. So after the end of this presentation, if you have any concerns, opinion, feedback, whatever thoughts, please send me an email. That would be really appreciated. So let me start with the cover story of The Economist published in May this year. So what do you think about the most valuable resource in the world? A century ago, actually, the answer was oil, but probably these days the answer is the data, the oil of the digital era. So simply, the data is everywhere. So recently, we have observed exponential growth of data. So whether you are running, or whether you are watching on TV, or whether basically just sitting in the traffic, virtually all activities create digital traces through your smartphones, smartwatches, or even cars connected to the internet. Now, some people estimate that in near future, self-driving cars will generate 100 gigabytes per second data, which is very huge. Then, what can you do with such huge volumes of data? We can extract values from the data. So by using some advanced technologies like a big data analysis or some artificial intelligence like a deep learning, the values can be extracted from data. So for example, we can predict like whether when a customer is going to buy something or when a person is at risk of a disease. Such things can be possible from data. So here, actually the question we have to answer is then how we can store such a huge amount of data and how we can process them to extract values efficiently in a timely manner. To be able to do that, actually, it is obvious that we need some infrastructure that can keep up with the volume and the velocity of data. So here, this is the place actually where the flash SSDs can play an important role. So now I'm going to show you one storage server we can find from Open Compute Project. Open Compute Project is the organization where that shares some designs of the various data center components among companies. So to store such a huge amount of data, obviously we need many flash SSDs like this. And some of them are grouped together and then connected to PCI switches. Then the PCI switches are connected to the root complex of the host machine, where the CPU and DRAM do exist. So of course, actually, we can think of building a specialized server where all the flash SSDs are directly attached to the server via PCI slots. But building such a specialized server actually is expensive. So in this example, let me keep assuming that we're going to use this commodity server architecture that can be easily found in many data centers. So if you want to store more data, then we can easily scale up by adding more flash SSDs into this architecture. But as increasing the number of flash SSDs, we'll see higher cost of moving data from storage side to the place where the compute is performed. So to have some better understanding, let's do some math, just simple math. So if you look inside the flash SSD, usually the enterprise level flash SSD contains many flash channels where the flash memory is attached. So in this example, let's assume we have 32 flash channels like that. Then, in a single flash SSD, 32 channels, and each channel can keep up with roughly 500 megabytes per second. So internally, inside the flash SSD, we can expect maximally roughly 16 gigabytes per second. And in this architecture, we have 64 flash SSDs. So the total aggregated internal bandwidth would be roughly 1 terabyte per second. But on the left side, actually, the host interface is going to be only the 16 gigabytes per second. So there is a huge throughput gap between the host interface and the aggregated internal bandwidth. So how can you leverage such an amazingly fast, ultra-fast internal bandwidth? So one solution we can think of is actually make the SSDs programmable so that we can do some computations inside SSD. So actually in data centers, many components are programmable. So I think the software-defined management is kind of an inevitable trend. And one example can be found in networking space. So if you think about the networking router or network interface card, they are programmable. So a new type of management for enhanced functionalities like a deep telemetry or security or more granular traffic management is possible. Another example of the software-defined paradigm can be found from the graphic cards. So initially, the graphic cards were born out only for the multimedia applications. So they shipped with hard-coded multimedia functionalities. But now, the graphic processing unit GPUs became fully programmable, and as you know, those GPUs are being heavily used for a new generation of applications like deep learning. So like this, actually making some components in data center programmable, the rapidly changing requirements in data center can be supported without physically changing the hardware itself. The next target is storage. But unfortunately, actually, such programmability is not ready, is not available in storage yet. So I think there's some major disconnect in terms of the innovation speed between the application and operating system running in the cloud and the cloud storage infrastructure. So if you think about the cloud infrastructure, cloud world, the application and operating systems are patched every few weeks for the new functionalities or new bug fixes. But the storage devices are not replaced with new ones during their life cycle of 3 to 5 years. So here, the matter is actually the software inside storage is written by device vendors as a proprietary firmwares that are not open to general application developers. So the application developers are gonna stuck with a device whose functionality and capabilities is frozen over time, while the software, many of the software actually inside storage can be customizable for better performance. And also, if you think about the period of 5 years, that is something like eternal in cloud world, where the new platforms, new features, new APIs are evolving in orders of months, and also some application demanding requirements to storage infrastructure grows very quickly. So here, I think that by making some storage programmable, we can better bridge the gap between the application and operating system needs and the storage limitations to innovate in-house at cloud speed. So now, let's think of the flash SSD a little bit. So flash SSD, the very natural question actually we can ask is actually whether we can use existing flash SSDs as a programmable device to run some user applications. So so if you think about today's NAND flash SSD that are available in the market, so left side there's a host server, and this is a different type of the flash SSDs, PCIe flash SSDs with different form factors. So even though these days these flash SSDs are being used as block devices, as a replacement of hard disk drives, but these are not dumb devices like hard disk drive. So if you look inside the flash SSD, we can find two key components, the storage media and some compute components like that. As I mentioned in the previous slide, even in the single SSD case, actually we can expect some throughput gap because enterprise level, there's some 16 to 32 channels and 500 megabytes per second. And on the other side host interface, if you assume that 4-lane Gen 3 PCIe, we can expect like a 2 to 8x throughput gap between these two guys. And also in SSD, there is some embedded processor and some amount of DRAM to run some SSD management tasks. So simply what I want to say here is the SSD is kind of a mini computer. So we can, by using some resources like that, we can run some usual applications. So for the last couple of years, actually, they're having some efforts to use existing flash SSDs as programmable devices. So I think the first effort was interest in the Smart SSD project. So if you're more interested, you can look at this paper query processing on Smart SSDs. And actually, this is the project I did for my last chapter of the thesis. So at the time, we thought it would be possible, but we are not sure whether actually this is possible. So our goal was to explore the opportunities and challenges of using a flash SSD to run some applications. In particular, in the scope of this project, we focused on some database operations. So here we use Samsung SAS SSD, and we modified SQL Server 2012 to offload some database operators, and then run them on the SSD. For that, we implemented selection and aggregation functionalities and then compiled them with the firmware of the SSD. So basically, this diagram shows how it works. On the left side, the base case, so if the SSD is just used as a block device, then obviously data has to be fetched from the device to the host machine. And then some necessary computations like scanning, filtering, and aggregations are performed on the host machine. But on the Smart SSD case, right after fetching data from storage media, the flash memory media, we can apply some operators like that, and then only results can be transferred to the host machine. Then some residual computations are done on the host machine. So in this environment, we ran TPCH Query 6 and got some little performance improvement and some energy savings. So even though we observed some opportunities of this approach, we also encountered a lot of challenges. The first challenge was actually device became a performance bottleneck. In particular, in this case, the low performance embedded processor without L1, L2 caches, and the high cost of accessing DRAM inside SSD randomly easily became a performance bottleneck. And also, the development environment needed further development. So, as I mentioned in the previous slide, actually, the aggregation and selection functionalities were compiled with the firmware of the SSD. So whenever something changes, actually, we have to compile them with the firmware all together and then apply the new firmware to the SSD. Another problem was actually to debug the application running inside SSD, we had to use some hardware debugging tool, which is much primitive than general software debugging tool like a Visual Studio, which is more familiar to the application developers. And 3 years later, actually, so there's another interesting project, EuroSQL. The goal of this project is to accelerate the data-intensive queries by using some embedded processors and also by using some hardware pattern matcher available inside SSD. So the authors actually used the existing Samsung PCIe SSD, and they modified a variation of MySQL and to do some early filtering inside the SSD. And this is much better than the previous work, actually. They developed some framework, and this is briefly described how the framework works. So there are some ISC tasks. ISC stands for in-compute storage computing, I think. So how it works is actually once all the inputs of one ISC I'm sorry, actually. The ISC task is the unit of the task that is runnable inside SSD. So all the inputs of one ISC task are received, then the ISC task does something by using those inputs and generates some outputs, and those outputs are passed to different ISC tasks. So as you can see, this framework follows the data flow model. So with this framework, actually, they modify the variation of MySQL and then do some all the filtering inside SSD, and actually got very nice performance improvement. For example, this simple filtering query, they got like more than 10x performance improvement. But still, actually, there were some challenges. Still, I think the computing resource is not powerful enough to run the usual application. So in this project, actually, they used two-core embedded processor. The speed is 750 megahertz, which is far weaker than the speed performance of the Intel Xeon processors usually used for the servers in data center. And also, if you think about the big applications running in the cloud infrastructure, those applications have been developed for the several years. So redesigning some components of such application for new data flow framework is not that easy. So I think it would be much better if some portion of the existing application can be runnable inside SSD with minimal efforts, meaning with minimal code changes. So in the past efforts, actually, we observed some challenges. So first, the existing flash SSD does not have enough spare processing power. To me, this is obvious because for the packaged SSD, there's no need to add additional resources more than to run the internal management tasks. So such low performance embedded processors are just enough. And some embedded hardware architecture has some limitations. And also, more importantly, I think the programming tools are not friendly to application developers. And those prototypes were not available to the application developers. So even though they wanted to test something and modify their applications to use such devices, it's not that easy because the devices are not accessible easily. But fortunately, actually, there have been some changes that help us explore SSD programming in a better way. So I think the first trend is the processing capabilities available inside SSD is getting powerful. So not embedded processor, just general purpose, low power, multi-core processors, and multi-gigabytes of DRAM, and also some hardware accelerators that where the compute-intensive tasks can be offloaded. And more interestingly, actually, compared to the past, it's getting much easier to program SSDs with the trend of moving towards server-like operating system like Linux, running on top of the general purpose in SSD processors compared to the proprietary firmware operating system running on the embedded processors. So I think that this is really important because by using the server-like operating system, the application developers can leverage existing tools, libraries, and expertise actually, and they can just focus on their own work instead of spending tremendous amount of hours to get familiar with the low-level embedded development work. So these two disrupt trends actually enables a SoftFlash project, and then this became the basis of this project. So what is the SoftFlash project? The SoftFlash project the goal of this project is to embrace Flash SSDs as a first-class programmable platform in cloud data center, to add some custom capabilities to storage over time, and better bridge the gap between the application operating system needs and the storage limitations, to eventually innovate in-house at cloud speed. So in SoftFlash project, we provide three components: hardware prototype, and software framework, and application. So in the next following few slides, I'm going to explain each component of the project in detail. So first, the hardware prototype. So in this project, we are using hardware called Dragonfire card. This is a programmable SSD, and then designed by Dell EMC and NXP. NXP is recently acquired by Qualcomm. So this device is actually only developed for the research purpose, and different forms of non-volatile memories can be attached. And this DFC card actually has the two separate boards, the main board and the storage board. And we are not the only team using this card. Actually, there is some open source community using this card, and there are many other universities and doing some interesting researches by using this card. So if you are interested in, you can go to this website to see what kind of interesting researches are going on. So this is the main board of the card. So there is the one 4-lane PCI Gen 3, which is used to connect to the host machine. And there's a 4-lane PCI Gen 3 that is used to attach the storage board I'm going to explain in the next slide. And also, actually, there are some 4 ports, 10 gigabps Ethernet, which supports RDMA, and 8-core processor, 16 gigabytes DRAM, and there is some hardware accelerator, so you can use some compression engine, encryption engine, and pattern matching engine. And there are 2 different types of storage boards. One is the DIMM adapter, and the other one is the M.2 adapter. So in DIMM adapter, we can there are 4 DIMM slots, so we can plug in a flash memory to DIMM slot. And there's FPGA for storage controller. So in case of the M.2 adapter, we can just plug in publicly available any M.2 like that. So these 2 different types of storage boards provide different flavor of doing some the research. So let's do a simple method again. In early slide, we saw that there's some big throughput gap between the host side and the internal SSD internal aggregate side. But also, if we compute the compute capability gap, there's also a gap like that. So in SSD, it has a 1.8 gigahertz, 8 cores, and 64 SSDs. So we can expect like a 900 something gigahertz. But on the host side, in this example, we use just 20 cores. So it's going to be slightly less than 50 gigahertz. So we can expect like a 20x the compute capability gap. Also, we can enjoy some more DRAM and hardware accelerators available inside SSD. So now, this is the software framework. So I'm not gonna go into too much details of all the software framework, but interestingly, we are using the Linux. So some containers like Docker can be running on the inside the device. And we have some SDK and library that allows to cross-compile the applications on the host side. And also we have some drivers that enables application to easily access the available hardware accelerators available in SSD. And also, if you see the leftmost box, the flash translation layer is provided and built in. So actually this device can be used as a regular device, regular SSD as well. So if we follow the leftmost path, it just works as a regular SSD. And if we follow the middle path, it's used as a programmable SSD. So now let me talk about some application scenarios actually we can think of by using this programmable SSD. So now I'm gonna explain 3 possible value propositions. The first application is the obvious near data processing. I mean, the moving compute close to data. So if you think about the big data analysis, the need to analyze the big data is imposing a shift from traditional compute-centric model to the data-centric model, which means in many big data analysis scenarios, the performance of the big data applications is not dominated by the execution time of doing some arithmetic instructions, but it is dominated by the requirement to handle larger volumes of data or the cost of moving data from storage to the place where the computing is performed. So by moving compute close to data, we can reduce the data that has to be traveled across the storage network memory CPU for compute, and also we can enjoy the fast internal bandwidth and the low latency, access latency to storage media, because we can directly access the storage media inside SSD. So I'm going to revisit this application in later slides with some real example. And another application we can think of is Agile and flexible storage. So the full programmability, I think we allow the storage interface and the feature set to evolve at cloud speed. So, I mean, if the application wants to use SSD beyond the block interface, then if the SSDs are programmable, then we don't have to actually convince the standardization bodies or the storage vendors to implement that. We can just expand the storage interface to based on the requirement for the application. So I think the one good example is a stream array of Flash. So let me briefly explain what is it and how it works. So there are two data streams, data stream 1 and data stream 2, and they are both incoming to a single SSD. And on SSD, there's two erase blocks. I mean, as you know, erase block is the smallest unit that can be erased on Flash. And each erase block is consisted of actually 8 Flash pages like that. So on the Flash side, actually Flash SS side, there's no way to distinguish whether data is coming from the data stream 1 or data stream 2. So eventually they are mixed together like that. And if the data stream 1, the data belonging to the data stream 1 is deleted, they will have some holes like that. To reclaim those holes, what happens is actually inside SSD, the garbage collector kicks in and they move the valid pages, those two blue valid pages to somewhere else, and they erase the whole block, which reduce the device performance and increase the RAR implication, resulting in reduced device lifecycle. So if the SSD is programmable, then we could do better. So basically, when sending the data streams can be tagged with a RAR stream ID, and inside SSD, based on the tag ID, we can collect data belonging to the same data stream. And once in this example, once the data belonging to stream 1 is deleted, then there's no there's no activities actually copying valid pages to different place, because all the pages belonging to the erase block A are invalid. So in Azure, the Microsoft Cloud actually wanted to this feature about 4 years ago, but until the end of the last year, when I checked, this feature hasn't been standardized yet for the NVMe, and even this is standardized. I think we might another year for the perspective of the data center operators. We might another year to make some purchase plan to buy devices that support this kind of functionality, and we might need additional years to modify our some applications to use such functionality. So by making the devices fully programmable, I think we can make some more economically right strategy by using some existing Flash SSDs. The last application we can think of is actually secure computation. The security is really important, as you know, and usually this is a topmost concern when enterprise CIOs decide whether to move data to cloud or not. So to realize the vision of secure computation these days in the cloud, the data is encrypted and stored on a storage device. But since there's only a limited number of operators that can be performed directly on the encrypted data, to perform some arbitrary computations, the encrypted data first have to be loaded from storage to the host and decrypted there, and then do some computation, right? But here, since the data have to be decompressed on the host side, that means actually temporarily, at least, the decrypted data, the clear text data, have to be present at various portions of data center infrastructure that is vulnerable to security attacks. So what we can do better here is that we can use the fully programmable SSD with the abundance of the resources to provide some trusted domain for secure computation by leveraging the cryptographic engine available inside the SSD. So we have encrypted data on SSD, and the cryptographic key is also stored on SSD. And if we need some computation, then decrypt the data inside the SSD, not outside the SSD, and do some computation and then only return results back to the host machine. So in this model, we can do the secure computation inside SSD, and the clear text never leave the flash SSD. So I think the secure computation can be done in better way with a programmable SSD. So far we have I've explained 3 value propositions we can explore by using programmable SSD, the moving compute closer to data, and Agile flexible storage, and secure computation. So let's a little bit more focus on the first value proposition, the moving compute closer to data. So this is actually the things I already mentioned in the previous slide. For the big data analysis, we need to fetch large volumes of data. But with the programmable SSD, we can do some computations inside SSD by leveraging the high bandwidth available inside SSD. Also some ARM cores and hardware offload engines. Also, actually, we can expect some energy savings by using more energy efficient ARM processors, and by offloading some computations from the host machine, we can avoid using expensive Intel Xeon processors on the host machine. So we might be able to think about a more balanced server with a lower cost of ownership. So traditionally, actually, this shows how the big data analysis works. So very simplified version. So on the bottom side, there's a storage cluster, and the upper side, there's a compute cluster. And each cluster has some compute nodes and storage nodes. So usually the size of data is big. Data first needs to be compressed and stored on the encoded and compressed and stored on the flash SSD. So after loading the compressed data from storage cluster, the first thing we need to do is we need to decompress the data and decode the data before doing some computations. So those B and C, the decoding and decompressing, both requires a lot of cycles from the Intel, the host server processors. And after decoding the data, we can do some processing, require the computations like filtering or aggregation or something else. But with the programmable SSD, what we can do is after fetching the data from storage media, we can do decompressed data inside SSD and decoding SSD in SSD, and partially do some computations that are not that compute intensive inside SSD, and then only results are moved back to the storage compute cluster, and the residual computation is done on the host side. So we pick up on open source data warehousing software, which is Hive, which is well known and widely used in industry. So in Hive, actually, they encoded the data based on data types. So it supports run length encoding and dictionary encoding, and also it supports some compression by using the zlib or snappy coding. So what we did was we compiled the source code. Cross-compile the source code for the ARM processors with the minimal code changes, and also replace some parts of the compression part to offload the compression work to the dedicated hardware engine to see how much performance we can improve by offloading some compression work to the dedicated hardware accelerator. So in this chart, this shows the performance of the scanning on zlib compressed initial data set on an x86 server and inside the programmable SSD. And for the fair comparison, we restrict the number of cores to just a single core. And this chart, the y-axis shows the throughput, millions of rows per second. And then there are three graphs. The leftmost is when all the application is running inside the x86. The middle one is when the application is running is the programmable SSD, but only the ARM cores were used. Single ARM core was used. And this guy, the same thing with the middle case, but the decompression work was offloaded to the hardware accelerator. So if you compare the first bar and the second bar, we got a slowly worse performance, which is expected because the ARM processor's performance is worse than the Intel Xeon processor. But by offloading some decompression work to the dedicated hardware engine, we got some like a roughly 5x performance improvement. So one thing to note here is that this is just a single device, single core performance. But in actual storage server, we use multiple SSDs altogether. So if we use the multiple SSDs, like more than 40 or 60 SSDs altogether, then we can get much higher performance improvement. So I think that adding more resources into the flash SSD does not increase the cost of the flash SSD huge, because in current SSDs, the most of the cost is actually dominated by the flash memory cost itself, and adding the ARM SoC will increase the cost about a few tens of dollars, but they can be easily amortized over the large deployment to the data center. And this is kind of just my kind of brainstorming. And in future, we may be able to actually, instead of buying the packaged SSD, we have some partnership with different vendors, and then buy some storage media from different vendor, and then buy the embedded processor or the processors from different vendor, and then collect them all together. So this way, actually, so I think the software hardware innovations in future can proceed like what we have for the PC ecosystem in several years ago. And I think the Google is already building their own SSDs by using this kind of model. So in future, beyond Google, many companies might consider this model to make their own SSDs for their own applications. So another opportunity we can think of by using the programmable SSDs is the storage disaggregation. So storage disaggregation in data center is getting challenging, and but here what you can do is by using SoftFlash, the programmable SSD. One host can access any remote SSD without involving the remote host access. So in our prototype, it has some network interface. So by using the network interface, what you can do is one host can access not local SSD, but some remote SSD by using this RDMA feature. So we can reduce this latency issue by using this model. And also, since the devices are programmable, then we can think of more larger scope of the storage interface beyond the block interface, so like a key value store or distributed stream. So the SoftFlash project actually is to create some software-defined storage substrate of flash SSD in data centers, and then use those programmable SSDs for the applications running inside the cloud data center. And this is possible by the recent distro changes, the ease of the programmability inside SSD and the abundance of the resources available in SSDs. So I think we are still in a very early stage. So I think hopefully next year we can present more interesting results to you guys. Yeah, thank you. So if you have any questions, yeah.
Okay, I just want to make clear that still you mentioned the stream-aware SoftFlash. That's good. Actually, for the update, right now multi-stream is NVMe standard. It is released NVMe 1.3 spec already, and also multi-stream features is integrated in Linux kernel version 4.13. That is also released already. Okay.
Okay, thanks for the clarification. Yeah.
So what was the cost of doing this on the SSD? So for instance, you basically added a considerable software stack to the SSD itself by putting an operating system in and putting all these engines in. Did you observe any increase in the average response time?
So actually, currently we are focusing on the bandwidth, the performance improvement, not the latency. So there's some preliminary results actually when you run some key value stores inside SSD as well. So we, in that case, actually we save some round trips between the host machine and SSD by doing some computation inside SSD. So it depends on the actual workload and then experimental environment, but we observe some 2 or 3x improvement for the latency side as well. So, but the key is actually how many times we can save, how many round trips we can save by doing some computation inside SSD. That's the key for saving the latency.
So, sorry, I misunderstood. The average response time should be a little bit higher, I would expect, right? Unless you're, you're able to deliver higher latency because there's less queuing on the device.
So when I say
because there are fewer requests.
yeah, but when I say the latency, it's the application side latency. So latency of handling one request.
Right.
So usually that latency contains some multiple round trips between the host machine and the device. So when I say the latency savings, actually that part, yeah.
So it would be very interesting. I know you're still developing this. It would be very interesting to see what the impact was on the device side.
Sure, absolutely, yes.
When you're advocating putting more processing power inside the SSD, were you thinking of having the SSD controller have a more powerful processor inside embedded in, or were you thinking of having a processor separate from the SSD controller along the SSD card?
That's a good question, actually. So I think it depends on how we want to use actually flash SSD. I mean, if you want to flash SSD as a for the two modes altogether, the regular SSD and the programmable SSD, then probably I think there have to be some dedicated embedded processors for the regular SSD management and some separate processor for the programmability. But if we want to use the SSD only for the programmability, then just having the powerful low power ARM processor will be fine. Yeah.
I think consider to use the bridges. The bridge between the regular SSD and the bus, the NAND bus, you put 3 pins in between.
Yeah.
They increase the power of the bridge.
Okay. So you mean the bridging between the host machine and SSD?
You put a bridge. The bridge NAND in and NAND out. You increase the process power of the bridge to handle this.
Probably, yeah, might be, but I haven't actually measured the exact additional power consumption for that. So I think that's a really good point. So we haven't got to the point to measure the power consumption yet. So, but that's actually one thing actually we need to definitely consider when measuring the power consumption the later stage.
Well, I'm actually from ARM, and I think when I've seen some of our partners working in this area, the challenge is what level of performance do you require in that intelligent drive? So obviously you can have just a single ARM processor or multiple clusters. I just wondered if you had any ideas of how to scale that work. How much performance do you need? Is it as much as possible? Or for some applications, is it quite small?
So that's really another good question. So I thought about how the GPU handles that kind of requirement these days. So if you think of the GPU, there are multiple different types of GPU cards available, right? It's a little bit less powerful and they're really ultra super powerful. So we might be able to actually build such devices with a different level of powers, and they use the devices based on the application requirements. That can be one model, I think.
Earlier in the presentation, you talked about random DRAM accesses.
Yeah.
So what are your thoughts about how to address that in the SSD?
So that was actually, I think that you were talking about the smart SSD project, the high cost of the randomly accessing the DRAM inside. So So that's why I think if you want to run some server application inside SSD, the environment available inside SSD has to be similar to the server environment. So that's why I thought the embedded processors without L1 and L2 caches are not enough to run the applications inside SSD. So going back to your original question, the high random accessing cost was one part of the reason was actually because there was no L1 L2 caches. It increases whenever we need some data, we have to access the data from the RAM. But having ARM processors actually supporting L1, L2, L3 caches, that latency could be dramatically decreased. Yeah.
I have an opinion that maybe the biggest problem with this is getting the flash vendors, the big flash vendors like Samsung, to release the chips, because they're seeing that a lot of their secret sauce in devices, of course, is the software and the firmware.
Yeah.
And so why would they give up? So are you seeing a shift from the vendors, from the fab plants that are going to open this up, or what about the political?
Yeah, right. So that's another good point, actually. So there's a big political issue here. So the storage vendor side, they want to do everything in the storage side, but the application side, actually, they want to, like Microsoft, we want to do something on our side. So there's some fight between these two kind of vendors. But when I started this project, about 3 or 4 years ago, for my thesis, there are not that many storage vendors that can provide high quality flash SSD memory and controllers. So right after publishing this paper, I started working on that. But now something has changed. I saw there are some ventures that provide high quality flash memory controllers, and we are partnering with one company getting a memory controller as well. So going back to your question, something has changed compared to past, and there are beyond the big giant storage vendors, there are some small ventures that can provide really good, awesome, high quality storage. Yeah. Yeah.
Hi, I'm Samsung, so I'd like to.
Yeah. So, okay.
I'm Robert. It's great to see you all. Thank you for the work that you're doing. Samsung, the easy way to understand it is we at our fab company, we want to sell a lot of NAND. So we'll cooperate with anybody that wants to sell a lot of NAND. So thank you for your work. And there will be, as you've already explained, an evolution where you put stuff in front of NAND as an FPGA, in front of NAND as a separate ASIC, and then eventually as an integrated ASIC. So this is the normal march. We've seen this many times, and we love what you're doing. So thank you.
Thank you so much. Okay, so I'm gonna be here on the whole conference week. So if you have any questions, again, the feedback, concerns, anything, please let me know, and then just ask me offline. Thank you so much.